So Addie asked a question in class, and it was about finding these guys by inspection. She asked me if I switched these last two numbers here, what would happen? And I said, well, I think it might work out, but I'm not really sure. So I checked, and it turns out, so you only want to put the numbers here that would be representative of an irreducible representation, like A1, for example. But you have to have the numbers here match. So if you switch these two, you would have this row with only one negative. And if you look up at the C2V character table, which is up here somewhere, you see that if there's a negative, there's always another one. And so if you would have switched those two numbers, you would have known that you did something wrong because you wouldn't have been able to find either one of those sets of characters in the character table. Does that make sense? When I do this, I usually start with A1. I always know that there's going to be A1 or whatever the most symmetric, irreducible representation is. There's always one of those, and so that's where I usually start. And you'll be able to see why when we go through this again today for BH3. What we're going to do today is basically go through the process again for BH3, and so the more times you go through this process, the more clear it becomes. And you were able to watch the video? So good. And I just want to mention that the first exam is a week from Friday. Make sure you have things clear. I will be available this Friday for help at 8 o'clock or whenever you need. I teach at 10. I teach organic chemistry, and then I probably have some time in the afternoon if you really need me. Just let me know ahead of time. But it is a week from Friday, and we will be having it on Friday. Make sure you prepare. It will be the questions will be very similar to what you've seen in the homeworks. So today we're going to talk about constructing molecular orbital diagrams again, and we're going to talk about the applications of symmetry, or one of the applications of symmetry in group theory, and that will be vibrational spectroscopy. So I asked you to try, or just think about, constructing the molecular orbital diagram of BH3. Eddie, were you the one that told me you thought maybe you did it in Pecan?
I probably did, but I didn't.
Okay. That's all right. Did anyone try to do this?
I tried, but
Okay. Good. I'm glad that you tried. That's all I wanted you to really do. So let's go through the process, and if you want to whip out that SALCS handout you have, or remember the numbering scheme that we used last time. I'm going to use the same numbering scheme while we go through this. When you're doing BH3, or any molecule, the first thing that you need to do is assign the point group. So what is the point group? I'm going to draw the molecule here. I'm going to assign an axis system, so the principal axis should be in line with the z-axis. So I'm just going to call this x, y, and then z is going to be coming out at you because the C3 rotation axis is the highest order. And as you said, this is you said D3H, right? It's C3 clockwise and C3 counterclockwise. So there's only one C3 axis, but there's two operations. Okay, so there's two unique operations that you can do. That's what that means. Good question. Okay, so here's a D3H point group, and what I'd like you to notice is what are the symmetries of the orbitals on boron according to this character table. So the orbitals on boron that are going to bind with hydrogen, what are the ones that are available? We have the boron 2s orbital and the boron 2p orbitals, right? So the 2s orbital is represented by this, and so the s orbital on boron has A1 prime symmetry. The px and py orbitals transform together as E prime, and the pz orbital transforms here as A2 double prime. So in the end, when we get our SALCS, we'll probably expect SALCS to match some of these, right? Because if we're going to make a molecular orbital diagram, we need the SALCS to match with the boron orbital so that you can have bonding. So that's just something to keep in mind, that you can just look at the character table and you can say, okay, well, I'll expect my SALCS to match some of these symmetries, A1 prime, E1, and A2 double prime. I'm probably not going to get an an E double prime because I don't have any orbitals that match that. All right, so we know the point group. Now the second step is to predict the number of SALCS. And we do this by determining which orbitals in our ligand set, our pendant ligands, are available. So I'm talking about the hydrogens now. So which ligands on those orbitals are available and how many of them? Good, 3. So there's 3 total, and it's 1 for each hydrogen, 1s orbital. All right, so now we can expect 3 SALCS. The next step is to generate a reducible representation. To generate a reducible representation for the set of ligand orbitals. So I'm going to copy my D3H character table down here, or at least the symmetry operations. So I'm doing the reducible representation for the set of ligands. And when you do this, you assign, so the characters, I'm going to write over here, the characters assign 1 if it stays the same, or a 0 if it moves. So if it moves away from itself, you assign a 0, right? So we have 3 can be our maximum number. So what is the reducible character under E? Yep. So what about a C3 rotation? A C2 rotation? So 1. What about sigma H? Sigma H is the mirror plane that's perpendicular to the C3 axis, so it's going to be in the plane of the molecule. What about an S3? It's a 0, because the first part of an S3 is to do a rotation. So just like the C3, for S3, you have a 0, because everything moves. What about for a sigma V? Sigma V is in line with the principal axis. Yeah, so there's 3 different sigma V's for each bond, boron hydrogen bond. So there's sigma V here, there's a sigma V here, and there's a sigma V there. And those are all they're coplanar with the principal axis and one of the C2 axes. Okay. So 1. Now, we're going to break this down into the irreducible representation. That's the 4th step. Break the reducible into irreducible representations. And again, you can do this by inspection. So if I started with my most symmetric my most symmetric irreducible representation here, which would be A1 prime, 1, 1, 1, 1, 1, 1, then I can try to figure out what these numbers would be. So if I just try to add these up, so if I'm expecting 2 different things, for example, this would be a 0, this would be a -1, because 1 plus -1 is 0. This would have to be a 2, this would be a 0, this would have to be a -1, and this would have to be a 2. And notice that that matches this E prime. Because you have to add 1 plus something to get to 3. Now, I have 2 irreducible representations here. Do I have 3 SALCS? Remember that these A and B irreducible representations are 1-dimensional, and that the E irreducible representations are 2-dimensional. So this is 2D and this is 1D. Okay, this E actually counts. It will for two things. So it will give you two different SALCs, and you know that from this 2 under E. Okay, so we've already found the symmetries of the 3 SALCs, even though we've only got 2 irreducible representations there. That's something that's tricky to remember sometimes. Now, I want to show you the systematic way to do this. So if you don't want to do the breaking down of the reducible representation into irreducible representations, if you don't want to do that by inspection, there's a formula. And I'm going to write it down here. So the system I just used, I refer to that as doing it by inspection, by just looking. So the number of irreducible representations of a given type is equal to 1 over H. What's H? The order of the group. What's the order of my group here? If I don't show you the character table, you can, well, if I don't show you the one up there where it's actually written, you can count. There's 1E, 2 C3, so that's 1, 2, 3, and then 4, 5, 6, 7, 8, 9, 10, 11, 12. So you count up all of the symmetry operations, not the symmetry elements, okay, but the operations. So the numbers in front of those symmetry elements counts. And that's your order. So it's 1 over the order times the sum of the number of operations in the class. So what I mean by that is the number in front of the operation. So this 2 in front of C3, this 3 in front of C2, and this 2 in front of S. So all of the other ones would be 1. Okay, so those numbers in front of my symmetry elements are the numbers of operations in that class. So E is a class, C3 is a class, C2 is a class, etc. You multiply that number by the character of the reducible representation. And by that, I mean these numbers. So here, 3, 0, 1, 3, 0, 1. So those numbers up there. And then you multiply that by the character of the irreducible representation. And the irreducible representations are here, we just wrote them. So for the 2, we might as well just do the 2 that we just found. If I were going to do this from scratch without doing it by inspection first, I would look up here at the symmetries of my boron orbitals, and I'd probably start with those because those are the ones that I'm going to expect to have. But let's just do A1. So the number of A1s, A1 prime, is going to be equal to 1 over 12, which is the order of the group, times, and I'm going to I like to do these one type all at a time. So I'm going to put the number of operations in the class here. So 1, 2, 3, 1, 2, 3. So those numbers come from up here. The number of operations in each class. And then I'm going to multiply those by the character of my reducible representation. So I'm going to multiply 1 by 3, 2 by 0, 3 by 1, 1 by 3, 2 by 0, 3 by 1. And then I'm going to multiply by the character of my irreducible representation. So now I'm looking, this is the number of A1s. I go up there and I look at the characters for A1. So all of them are 1. I multiply each one of these things by 1 and then add them together. So this is going to be 1 times 12, 1 over 12 times 3 plus 0 plus 3 plus 3 plus 0 plus 3. So we have 1 A1. For E1, I do the same thing. The number of E1s is going to be equal to 1 over 12 times, I'm going to do the number of operations in the class first, then the irreducible representation. So now I'm dealing with the irreducible representation of the E prime. If you ever do this treatment and you come up with something that's not a whole number, that means there's a mistake. You should always get either a whole number or 0. We found our irreducible representations. Now, we could just draw our molecular orbital diagram, but I'd like to show you how to draw the SALCS first. So what do you do when you want to see what the SALCS look like? In your handout, this is number 5 and 6. I'm going to do 6, which is the more systematic way to do it. So what do the SALCS look like? And this is where you need to follow one of the ligands through all of the operations in the class. And it's important that you do all of the operations and remember, just like Addie said earlier, there's more than one operation in each class. So you have to draw out something called an expanded character table to do this. So it's useful to know what each one of these operations are. So I'm going to break the 2 C3s into a clockwise C3 and a counterclockwise C3. There's 3 C2s, and I can just call them C2, C2 prime, and C2 double prime. And this would be, I'm just going to assign, so if I draw my molecule here, so I'm going to assign numbers to each one of those hydrogens. So one of the C2 axes could be in the bond axis of the boron hydrogen 1. So I'm just going to call this hydrogen 1's C2 axis. Hydrogen 2 has a C2 axis, and hydrogen 3 has a C2 axis. We have 1 sigma H. There's 2 S3s, and the S3s correspond to the C3s. So there's a clockwise rotation followed by a horizontal reflection, and then there's a counterclockwise rotation followed by a horizontal reflection, and we'll call that S3 to the -1. And then there's 3 sigma V's, and I'll just call them sigma V prime, and sigma V double prime. And these again correspond to, they're in plane with the C2 axes. So I'm going to call them H1, H2, and H3, according to which bond they're cutting through. Okay, so this is my expanded character table. And now I'm just going to follow what happens to H1 under each one of these operations. If H1 stays the same, I'm going to call it H1. If it moves to H2, I call it H2. And if it moves to H3, I call it H3. So the characters I'm dealing with, so if H1, if it's does not move, H2, if it moves to H2, and H3, if it moves to H3. So, what's E? C3 clockwise. According to my drawing, H1 moves to H2. C3 counterclockwise, H3. C2 in the H1 axis. C2 in the H2 axis. And the other one, H2. Sigma H in the plane of the molecule. H1. S3 clockwise. H2. So it moves from H1 to H2, and then you reflect, which doesn't do anything to it. So S3 minus 1, so counterclockwise. Goes the other way. Sigma V in the H1 bond. H2. Sorry, sigma V in the H2. Yep. And sigma V in the H3 bond. Flux it to H2. Okay, so we've taken care of step 6. Now, step 7 was to project the irreducible representation characters from 4, so the 2 irreducible representations that we found, we're going to project those characters onto this table that we just made. So I'm going to write out my character table again. So what does my A1 prime look like? We go up to the irreducible representation that we found. Everything was a 1. So that one's easy to do. So I'm going to multiply A1 characters by the H1 table above. And the A1 characters, E is 1. All of the C3 is 1, so I'm going to draw 1 for each one of those C3s. All the C2s are 1. The sigma H is a 1. S3s are 1, etc., etc. And then I'm going to multiply that by the table above. So for E, I multiply 1 times H1. For C3, clockwise, I multiply 1 times H2. For C3, counterclockwise, I multiply 1 by H3, and so on. And then I add them all together. So if I just count the H1s, there's 1, 2, 3, 4. Yep, you're right. 4 H1s. If you counted up the H2s, you should get 4. You should have 4 H3s and 4 H4s. Oh, there is no H4. Just kidding. I'm trying to see if you're awake. Or if I'm awake. All right, so what does this tell us? It tells us that this A1 SALC, so the A1 prime SALC, has no nodes because all of the orbitals, or all the electron density is of the same sign. They're all positive. So the A1 SALC has no nodes. And it also tells us that the electron density has equal amplitude on each one of the hydrogens because each one of these hydrogens has the same coefficient in front. So the A1 SALC has no nodes and the electron density has equal amplitude on each hydrogen. So if we were to draw our A1 SALC, remember that our boron BH3 looks something like this. So each one of the hydrogen positions has equal amplitude of the same sign. And that is our A1 prime SALC. So let's do the E prime. Actually, before we move on to E prime, let's look back. This A1 SALC, what orbital on boron do you expect that to match? Just looking at it. The 2s, yeah. Let's go look at that 2s again. 2s had A1 prime symmetry. So that makes sense, right? So we might expect the E1 prime to have the symmetry that matches a px orbital and a py orbital. See if that's what we get. So E times H1 from the table above. So E is a little harder. You have to keep track of your numbers. For E, the character is 2. For C3, it's -1. So the 2 different C3s get a -1 character. For C2, it's a 0. So all of those C2s get a 0. Sigma H is a 2, I believe. Yeah. S3 is a -1. And the 3 different sigma V's get a 0. And now I'm going to multiply that by the table above. And then we have to add them up, see what we get. How many H1s are there? Oops. There are 4 H1s. How many H2s are there? Yeah. So now we subtract 2 H2s. And what about H3? Yeah, also a -2. So H3. Okay, so this is what going to give us some clues about what the two different E prime SALCs are going to look like. So what can we tell from this? Well, is there a node? Yeah, there's a node. Okay, so you can kind of think of this as a node. Two have the same sign, and one of them is different. So each of the SALCs are going to have one node. And what else can we say about the amplitude of the positive versus the negative? It is bigger on one hydrogen. Is it bigger in total? No. Yeah, you're right. So the total positive is equal to the total negative. So there's a couple ways you can try to do this. One, I'm going to draw here, and this might be the most obvious to you. So let's say that H1 actually has a bigger positive lobe than the two negatives. That one I can read directly from what we found. Did that look right to you? The other one's a little bit less intuitive, but it follows the rules that each cell has a node and the total positive region is equal to the total negative region. So instead of drawing electron density in all three atoms, we could leave the node actually in the plane of one of the atoms, where you have a positive lobe on one side and a negative lobe on the other, and those two things have equal intensity. Now, that's hard to find. There's two things that can help you. One is, remember that these SALCs were supposed to have matching symmetry to the px, this is px, and the py orbital on boron. So now if I draw my axes on here, or my bond axes, now it's kind of clearer maybe where these nodes are coming from. So the node here on this py orbital is right through that top hydrogen atom. So that's where the second SALC I drew came from. Matches the py symmetry, or px symmetry, sorry. Didn't draw that very well. And the py, the lobe that's the hydrogen that the py is pointing directly at would be the one with the most electron density, because that's the most favorable interaction, or the most direct interaction. And then these two guys down here are a little bit smaller because they're not end-on overlap. They're kind of side-on overlap. So that's one way that can help you find the SALCs. You can actually look at the orbitals that they should come from and try to match the symmetry of the orbitals with the rule that you just found. Or there's a table in the back of your book that you can look at. That will help you. So in the resource sections of your textbook, you will find character tables, and you will also find shapes of SALCs that you can use to guide you. On an exam, however, I expect you to know how to find the SALCs without looking at the table. You will have character tables, but not the table of the SALCs. Okay, so now we can make our molecular orbital diagram. Oh, and there's one more thing I wanted to correct about what I said on Monday. I was confused about the orbital energy levels when you're doing water. Mm-hmm. Yeah, so I was saying that oxygen S and P, right? And I wasn't sure where to put the hydrogen stops. So I think I put them like above the P. I looked at the ionization energies, and it turns out that oxygen and hydrogen have almost identical ionization energies, and so the highest energy SALC should be in line with the P orbital. I will just point out that if I know your book, the book is good at a lot of things, but this is one downfall of the book, is that it doesn't include hydrogen in a lot of the arguments for the periodic trends, or the tables for the periodic trends. I find figure 1.25 and table 1.5 on ionization energies helpful, and those are on pages 26 and 27 of the textbook. So those include all of the metals and the non-metals that we'll be dealing with. It's very useful because it includes hydrogen, and then it shows you the trends with hydrogen, and then all of the second period elements. Okay, so from the table, I know what the relative ionization energies from boron are compared to hydrogen. Can you guys guess based on periodic trends? Sometimes these periodic trends are a little tricky. I'm going to draw my boron orbitals over here. So with boron, I have an s orbital and an A1, which has A1 symmetry. Sorry, that's A1 prime. So I have a boron with A1 prime symmetry, and its s orbital. And then the px and py orbitals are transforming together with E prime symmetry. And this is supposed to be degenerate, but I'm going to draw it above. Is the pz orbital has A2 prime, double prime symmetry. So those are all, in the atom itself, those are degenerate. They're only different when we make the molecule. And it turns out that, do you think that hydrogen has a higher or lower ionization energy of boron? They have a guess. This is a tricky one. So it's the 1s, hydrogen 1s versus boron 2p, but it's the first electron in boron's 2p, and so it's actually really easy to take that guy out. So hydrogen actually has a higher ionization energy than boron, and so that means that it's easier to pick an electron out of boron. So you would draw your hydrogen SALCS at a lower energy than the p orbitals of boron. So I'm going to draw them here. I have 2 of E prime symmetry. I'm going to draw the pictures of them. And I have 1 of A1 prime symmetry. So when I draw this molecular orbital diagram, my A1s are going to combine pretty well. They're similar energies. So I'm going to have a bonding interaction and an anti-bonding interaction that both have A1 prime symmetry. E prime is going to combine, so my 2 E primes are going to combine with my 2 PX and PY E primes, and I will get a set of 2 bonding orbitals and a set of 2 anti-bonding orbitals. And again, this is where you don't necessarily know the relative energy levels of the E1 prime and the A1 prime. And I should have drawn little stars next to the guys that are antibonding. I'm going to draw it like this. And then I have my A2 non-bonding PZ orbital. And obviously this is not to scale. So I'm going to fill in my electrons now. So there are 3 in hydrogen. There was 1 from each hydrogen 1s orbital. And then there are 3 in boron. I should probably draw the ones in boron according to Hund's rule. And so then I fill in 6. Into my molecular orbitals, and that gives me a bond order of 3, which is exactly what I should expect for BH3. Okay, so there's a couple examples, I think, where I'm asking you to draw molecular orbital diagrams on your homework. They're hard, and they use they use these same concepts, but sometimes you'll have to apply them to a set of p orbitals instead of x. Sometimes you'll have to apply them to something that might seem a little bit more complicated. So please try it so that you can come ask me questions on Friday, because I think it's not that easy. But these are the sorts of things that you might see in your exam, so it's worth practicing. I will be available Friday afternoon as well. Okay, so now we're going to talk about applications of symmetry in vibrational spectroscopy. So the applications of symmetry that we mentioned were, we could apply symmetry to make molecular orbital diagrams, we could apply symmetry to make to interpret vibrational spectra, and then we could apply symmetry to understand chirality. So we're on number 2 of the 3 things that we talked about. Vibrational spectra, you should probably know, or you've heard of this before, IR spectra and Raman. So symmetry can help us with vibrational spectroscopy because it can help us determine the vibrational modes of the molecule. In fact, in group theory, you can account for every single vibrational mode of a molecule, and it's all right in your character table. And that's why symmetry is really useful when you want to predict peaks that you'll see in the Raman or the IR spectrum. Okay, so we're going to start with water again. Simple example. And we're going to determine how many peaks we might see in the IR spectrum and the Raman spectrum. So again, I'm going to give you kind of a stepwise process for doing this. The first thing that you do is assign axes to each one of the atoms. So if you think about vibrational spectroscopy, what's happening? Vibrations in molecules are just individual atoms moving in the X, Y, and Z directions, right? So that's what causes a vibration. So when we're looking at the motions of the atoms, we need to assign coordinate systems to each one of the atoms. So for oxygen, and I'm going to remember that this is the C2V point group, and my Z-axis is up in the plane of this molecule, so I'm going to draw my Z-axis on oxygen up, I'm going to draw the X-axis to the right, and the Y-axis is coming out and going back. I'm going to draw the same axis system on hydrogen, each one of the hydrogens. So because we're looking at the motions of each individual atom, we need to assign 3 dimensions or a coordinate axis set to each one of the atoms in the molecule. And then we're going to treat it very similarly to the way that we're basically going to find irreducible representations that represent the vibrations of the atoms in the molecule. So this was the first step, and it was to assign coordinate system. The second step is to find the reducible representation for all of those coordinates. So we're going to determine how these coordinates transform in the point group of the molecule. So remember, for an atom with for a molecule with n atoms, you have 3n coordinates. And that corresponds to 3n degrees of freedom. So when we assign characters to the coordinate axes, it's very similar to assigning the characters to any reducible representation. We're going to assign a 0 if the atom moves at all. So if the atom moves away from its origin, literally the origin of the coordinate system that we drew, it's a 0. If the atom stays the same, that's the only way that you can assign it a non-zero value, if the atom itself does not move. If the atom itself does not move and the coordinate system stays exactly the same, you assign 1 for each one of the axes that stays the same. If there's a reflection or a rotation that leaves the atom in the same position, however, rotates the axes or reflects the axes into the negative of itself, then you assign a -1 for each one of those axes. Okay, so as before, you're just going to rewrite the C2V operations. I'm going to write the C2V character table here. We have an E, a C2, a sigma V in the XY plane, and a sigma V prime in the YZ plane. And we need to find the coordinate, or the reducible representation for all of the 9 coordinates here. So for the E operation, what is our number? Everything stays the same, right? So it's 9. For C2, so we're rotating around the axis that goes right through the oxygen atom, and we're changing the hydrogen's position. So you rotate one hydrogen into the other. The hydrogens move, so you don't look at them anymore. Just ignore them because they have 0 value, or 0 character. The oxygen, however, has not moved out of its position. So those coordinates you need to look at. What's happened to the z-axis? Stays the same, it gets a 1. What happens to the x-axis? -1, and y? -1. So your total character is 1 minus 2. So it's a -1. What about sigma v in the xy? So we can define, so this is z, x, and y of the entire molecule. So in the xy plane, let's call, just be like before, let's call this the zy. We're going to change this. Why is that not working now? Yes, I should be xc. Okay, thank you. I wrote it wrong. Okay, so that makes a lot more sense. Now we're going to reflect in the plane of the molecule. What do we have? So all of the atoms are staying in the same position, right? Which of the axes are staying the same completely? And we would assign 1. Z and X. That's 2 from each atom, right? So we're going to have a positive 2 from each atom. And what about Y? -1. So positive 2 minus 1, we'll have a 1 from each one of the atoms. And so we'll get a total character of 3. And then sigma V prime is the one that we've been splitting the molecule in half between the 2 hydrogens. So for that one, what happens to the axes on the hydrogen? They move, right? So we don't care about them. So now we're looking at just the oxygen. So 2 of the coordinates stay the same, the ones that are in the Z and the Y. X is inverted. So we have 2 that stay the same, 1 that changes, so that's a positive 1. Okay? Then guess what the next step is? Get the irreducibles. Good. And for this one, you've got a big number here, 9. It is hard to do it by inspection, and so it's a lot better to just do it the systematic way with the formula. So I'm going to say that the number of A1s is going to be equal to 1 over H times. So I'm going to do first the number in front of the operations, which is all 1. 1, 1, 1, 1, times the irreducible representation of A1, which is also 1, 1, 1, and 1, and then the reducible representation 9, -1, 3, and 1. This gives me 9 minus 1 plus 3 plus 1, which is 12 over 4. And I forgot to put here the H is equal to 4. So that gives me 3 A1 irreducible representation. So now we need to find the number of A2s. And I'm going to, the characters for A2 are 1. Yeah, for the vibrational modes, you don't really, there's not an obvious way to, that I know of anyway. So I was just going to do A's first and then B's, but do whatever, you can do it a different way. It's okay.
I didn't know, I thought we just did like A and B on the
Oh, no. This, for vibrational modes, you might need to do all of them. So the characters for A2 are 1, 1, -1, -1. So for this one, you get 9, -1, -3, -1. So you should get 4 over 4, which is 1, A2. So you need to do the same thing for B1 and B2. And I'm going to cheat and tell you what it is. Save time. So you should come up with 3 B1s and 2 B2s. So now we've found the irreducible representations. Each one of them is a one-dimensional irreducible representation, and so this accounts for all of the vibrational, rotational, and translational modes of this molecule. So all of the motions. Now, since we're talking about vibrational spectroscopy, we need to subtract out the rotations and the translations. I'm going to go to the next page. So we'll have to subtract out 3 rotations, or 2 if it's a linear molecule, right? So rotational degrees of freedom or 2 if it's linear. And we can find these because these are the ones, these are the irreducible representations that have the same symmetry as the x, y, and z coordinates, and they're written, the rotational degrees of freedom are the IRs that have Rx, Ry, and Rz in the character table. We're going to subtract out the rotational degrees of freedom and the translational degrees of freedom, and there will be 3 of those. And the translational degrees of freedom are the IRs that correspond to, or they have X, Y, and Z coordinates in the character table. So, this will give us our vibrational modes. And you should probably be familiar with this. The vibrational modes are 3n minus 6 for a regular molecule and 3n minus 5 for linear. If you've had PChem, I'm pretty sure you guys have talked about that, maybe in general chemistry? No? Okay. Well, you'll see this formula soon. Any molecule will have 3n minus 6 vibrational modes. Unless it's linear, it has 3n minus 5, where n is the number of atoms in the molecule. So the vibrational modes for water are all of the motions, and we found 3 A1s, 1 A2, 3 B1s, and 2 B2s, and we're going to subtract out. Okay, so now it's convenient if you have a character table. I'll look at mine. And I wish, how do I get rid of this toolbar? Does anybody know? Little thing on the side. I don't want to see that. Maybe. Show hide. Navigation panes. Hide toolbars. Oh, I'm afraid of that. That's probably going to screw me up. Oh, cool. Thank you. Okay. Okay, so where's our C2B? Here it is. And so you can see here that we're going to subtract out. So let's just look at the rotations at first. So rotations for A2, B1, and B2. So we're going to subtract out one of each for the rotations. And we're going to subtract out one of each for the X, Y, and Z coordinates. So we're also going to subtract out an A1. We're going to subtract out another B1 for this X and another B2 for the Y. So in all, we're going to subtract one A1, one A2, two B1s, and two B2s. So I'm going to subtract one B1 and one B2 and one A1, which correspond to X, Y, and Z in the character table, which are my translational motions. And I'm going to subtract out a B2, a B1, and an A2, and those are for the rotations around the X, Y, and Z coordinates. Now, that tells me all of my vibrational modes, but you might remember, or maybe you don't if you haven't had PChem, there are some infrared selection rules. Only some of the vibrational modes are actually IR active or Raman active. So perhaps they'll look familiar to you. If a vibration results in the change in the dipole moment, it's IR active. In group theory, we can recognize this because there's an X, a Y, or a Z in the character table. So you look at the character table and you look for these things. So I'm going to go back to my character table. I never wrote the end of my math here. The total vibrational modes here are two A1s and a B1. So we can go to the character table and see if A1 or B1 are IR active. Oops, I don't need to scroll up, do I? I just need to go to here. So A1, is it IR active? It sure is. It's got a Z. What about B1? Is it IR active? Yes, it is. So we have two A1s and a B1. That's three IR active modes. Three IR active modes for water. We can tell what they look like based on their symmetries. The A1 modes, remember that A means that it's symmetric with respect to the highest order axis. Well, the two A1 modes are going to be symmetric with respect to the Z-axis. They are this one, when the water's going like this. No one's looking at me. Like when so my head is the oxygen and my fists are the hydrogens. They're basically bending and stretching, compressing and stretching. So this is a bend. Stretch. Symmetric stretch. The bend is when the two hydrogens are kind of wagging in and out at the same time, symmetrically. So they're doing this. Okay, that's a symmetric vibrational mode. The B1 would be anti-symmetric with respect to that highest order axis, and that's the one where the hydrogens are stretching anti-symmetrically. So one's going out while the other's coming in. So it looks like this. By my IR aerobics this morning. Okay, so there's a little bit more information about the stretches and their identities based on the irreducible representations that they come from. Now, Raman selection rule. If a vibration can result in a change in polarizability, it's Raman active. We can see this from our character table because it corresponds to any of the binary products. So we will see x, y, x, z, x squared, y squared, z squared, or a linear combination of these, or what, in other words, like x squared plus y squared, or x squared minus y squared. Those sorts of things in the character table mean that that mode is Raman active. So let's go back up to our character table, and we had two A1s. Are they Raman active? Yes, they are, because they have squares of the coordinates. What about my B1? Is it Raman active? It sure is. So now I have also 3 Raman active modes. Now, I want to point out one very important thing, and that is that these selection rules tell you what's possible, but not what is actual. So, I have 3 Raman active modes. I might only see 2, because in reality, 1 might be off the scale, or 2 might be overlapping. Okay, so they won't tell you literally what you'll see, but they can tell you what you might expect in the Raman or the IR spectrum. Okay, so next time we're going to keep on going with vibrational selection, or the vibrational modes, and I'm going to tell you another way that they can be useful, and that is by specifically like selecting out a type of vibrational mode. So like if you wanted to see the carbonyl vibrational modes, you could figure out how many carbonyl vibrational modes you could expect. So that's called selected vibrational modes. And then we're going to move on to one last section before the exam, which is solids. So we're going to talk a little bit about some semiconductors and some solid stuff. And then your exam will be on Friday. So let me know if you have any questions. Otherwise, I hope to see you on Friday, but if I don't, have a good weekend.